and welcome to this tutorial. In the tutorial which I'm just going to do for today is that I'm just going to start a chemical reaction of a given structures in the presence of the reagents and also a solvent. In this tutorial, I'm just going to later add heat, which is going to impact the thermodynamics of the reaction, to see that what are the possible outputs of this reaction that you may expect to have. However, before that, I'm just going to remind you that I'm just going to show you how to just conduct the chemical reactions in organic chemistry step by step. First of all, the thing which I know that as a kind of a key things in order to orchestrate a chemical reaction is that I have to be able to find a lone pairs of the electron that they are able freely to just migrate from one compound or one element to the another one. Actually, that lone pairs electron mobility, that's the thing which orchestrates the chemical reaction. Then, if I go back to look into this one, the thing which I'm going to look for is that am I going to see a lone pairs of the electron at least that is able to move between one element or one compound to the other ones. In order to do so, I'm going to focus on the left side. On the left side, I see that I have the bromide, which comes from the group 7 of the periodic tables. And from the group 7 periodic tables, I know that they are just a good living groups because after departure, they are just going to form a very weak base. Then as a result, I'm looking into this one. First of all, the thing which is obvious is that there is a huge contrast of the electronegativity between the central carbon which I have here and the bromide over there. I know that the electronegativity is just going to increase on the periodic table from left to right, from down to up. Then as a result, bromide is extremely electronegative, which means that it has a huge propensity to attract the electron clouds around itself. Then, this contrast of the electronegativity, it makes this bond extremely polarized. And also, I know that because the solvent which I have, which is a kind of an alcohol, which is ethanol, which is able to form the hydrogen bond, is going to induce the departure of the bromide. Because this is extremely electronegative, you're going to see that the electron clouds, due to the contrast of the electronegativity, becomes something like that. Then the bromide, with the presence of the polar protic solvents, which is the ethanol, is just going to leave. That's why we call them, they are a good living group. If they leave, then the question that we are going to ask ourselves is that, what is going to happen to the electron pairs that is shared between the carbon, the central carbon there, and the bromide atom there? Then, because the electron is much used for that, the electron which is shared between them is just going to migrate towards the bromide upon its departure. Then what do we expect? We expect that we have the bromide with 4 lone pairs of the electrons, which gives them the negative charge. We are going to see that it's just going to use that a little bit later. And at the same time, we are having these structures. I have the central carbon, which I have methyl groups around it, and the bromide which is there. However, the thing which is happening right now here is this, that I have to be able right now to find the formal charge. The key thing is this, in organic chemistry, whenever you form a bond or you dissociate a bond, regardless of the energy intake that you have to find the formal charge. In order to do so, I'm just gonna follow these very simple instructions. I'm just gonna say, okay, what is the elements that was directly impacted as a result of dissolving the bonds around it? And I see that the element which was directly impacted by doing so, it was this carbon. I'm just gonna put the dot around it. Okay? Now, then I'm gonna ask myself 2 questions. The first question is this. The element which is impacted by dissolving the bound, what is its address in the periodic table? By the address on the periodic table, it means I'm looking for the group that it belongs to. The group that the carbon belongs to is going to be group 6. The carbon is just going to belong to group periodic 6. It has 6 electrons, 2, and it comes to the group 4. It comes to the group 4. The other question which I'm just going to ask myself is that when I just put these dot net around the carbon, which belongs to the group 4, how many electrons is within this net? I see there is 1 here, there is 1 electron parts of this, there is 1 electron parts of this. Then you see that there are 3 electrons within this net which I have drawn. I'm just going to subtract it from the 4 which I had before, then I just got to the point to the number +1. Then as a result, I notice that the +1 which I get from here, it just signifies the formal charge of the carbon which was directly impacted by breaking the bound. Then as a result, I'm just going to put the formal charge which is going to be positive around the carbon. In terms of the technical terminologies, you can call the carbon which is positively charged as either a nucleophile or at the same time you can also call that a carbocation, or at the same time you can call it electrophile because this is positively charged, and the positive charge has an inherent propensity due to the electrostatic forces to be attracted to the negative charge. Then it likes the negative charge. That's why we call that electrophile. Electron represents a negative field. In Greek means loving. Then it loves the negative charge. Then the carbon positive which we got, we have 2 terms to use for it. Either we call that electrophile, electron loving, or also we call that a carbocation. Now, and also we just formed this one here like that. However, what do we have here? We see that we have sodium ethoxide, which is within the solvent of the ethanol, which I'm just going to warn you because in the next tutorials, I'm going to talk about the solvolysis. You're going to see the impacts of the solvents more in future, that they can attack also the carbocation that we have formed. But here, I'm going to draw your attention to the fact that the structures of the sodium ethoxide that you have resembles much to the ethanol that you have. Both of them comes with C2H5O, C2H5O. Now, within this one, you're going to expect that this structure within this solvent turns into 2 format. You're going to have C2H5O and A. Within the solvents that you have, it's just going to reach to an equilibrium. It is going to reach to an equilibrium that you're going to see that this one, it tends to be with 3 lone pairs. It's going to just grab the electrons from the sodium, because sodium comes from group 1 of the periodic table, and they do not show that much strength in holding back the electron. If that electron is going to be shared with them, then as a result, if you're having a fight between electron pairs which is shared between the oxygen and sodium, you're going to see that within the solvent, oxygen is going to grab that one and becomes negatively charged, and sodium becomes positively charged. Both of them, they are in aqueous format because they are in the solution. Then as a result, what you're going to expect is this, that these structures that we had, which we call that ethoxide in the solvent, because thanks to the presence of the solvent that we had, it becomes negative. It's just going to wander around within the solvent, because look at that. I emphasize that I have a solvent here of the same structural resemblance to the sodium ethoxide. I have also bromide there. I have also the sodium there. But the most important thing which I noticed here is that I have given rise to the presence of the ethoxide, which I see that it comes with 3 lone pairs of the electron, which they are not restricted with the presence of the resonance hybrid structures, which it restricts the mobility of those electrons that they are formed with the resonance structures. I see there is no resonance, which it means that these lone pairs of the electron, they are freely available to migrate to the other structures. And it comes also with a negative charge. Then look at this, what I have done so far. In this solvent, which was polar protics, because it was able to form the hydrogen bond to entice the departure of the leaving group, the bromide, what have I done so far? I have created empty orbitals of the carbocation there, because the positive charge on the carbon is representation of the empty orbitals, which is welcoming coming electrons. And also, I have given rise to the presence of 3 lone pairs of the electron, which are able to migrate. Then the goal which I had, in order to unlock it, there is a key always and the lock in the organic chemistry reactivity, and is that always the lock is this one, that you have to open it in order to show the empty orbitals for the electrons migration, and showing the electrons that they're able to migrate, which I have done it so far. However, you're going to see that these structures that I have formed here, besides the stable carbocations which I have there, you're going to see that this one also, we called that before Lewis base, because based on the definition of the basicity and acidity, you remember that any structures that it has a lone pairs of the electron, and lone pairs is going to migrate, it's willing to migrate, we just call that the Lewis base. But on the other hand, if there is any structures that is accepting that the lone pairs which is coming from the Lewis base, we just call that the Lewis acids, then from this perspective, you can see that ethoxide which I have, ethoxide ion which I have, a very strong Lewis base, because not only it has 3 lone pairs of the electron willing to migrate, but it also comes with a full negative charge. And also the other structures which I have here, which is the carbocation, it becomes a kind of a Lewis acid, which essentially you are just converting this reaction into the acid basicity reaction. Now what happens? Because of the negative charge that you have here, the positive charge is here, the basic electrostatic forces, it represents that these two are going to attract each other. And this is more facilitated because of the presence of the ethanol that you have. They can swim around in the solvent, get close to each other, and you're going to see that the lone pairs of the electron, which is present here, is just going to fill the empty orbitals of the carbocation. Then as a result, that's what we call that nucleophilic attack. And look at that. Make sure that you understand the direction of the attacks. Attack starts from the lone pairs electron. They are just going to, it shows a direction that the lone pair is going to just come to fill out the empty orbitals of the carbocations. If this happens, what do we expect? We say that if this happens, I'm just going to show that with the arrows to the right side. I have the central carbon here. I have the methyl groups spanning around it. I have CH3 spanning around it. Now, look at this one. I'm just going to erase this to just highlight it with the different colors. I'm just going to show this one with the different colors red, which it means that now the lone pairs which I had over there, when it is attacking the carbocation there, it's just going to show this itself as a shared electron. Now the red color now, it becomes the red, I should say, which symbolizes that this lone pair is spent to form the bond, and I know that the bond is formed from the oxygen. Then the oxygen comes here. Now, instead of the 3 lone pairs of the electron attaching to the oxygen, I have 2, because one of the lone pairs is spent to form the bonds. And now what else is happening? And I have also, I can see that I have this one, the rest of it. I can see that, okay, I have the oxygen, which it comes to, let's say, for example, I have Z2H5. Okay, and that forms what we expect. Now, in order to just complete this solution, now we come back to the main thing that we discussed. In organic chemistry, whenever you form a bond or whenever you dissociate a bond, you have to stop to ask yourself what is a formal charge or effective charge of the elements that are directly impacted by the forming of the bond or dissociating of the bond. You see that the oxygen and carbon, they are the direct elements that they are impacted by the forming of the bond. Then what I'm going to do, I'm just going to first draw a bond around the carbon here. I'm going to ask myself two questions. What is the address of the carbon in periodic table? This is group 4. How many oxygen, how many electrons I have in this dotted net? You see there is 1 electron there, there is 1 electron there, there is 1, there is 1. 4 minus 4, it gives me 0. It means that the effective charge of the carbon here, which previously was carbocation with positive charge, now it's reduced to 0. Now this is completely neutralized. Now we are just going to go to ask ourselves the second question. What is the other elements which is impacted by forming of the bond? We are just going to see that this is going to be the carbon, oxygen here. But you see there is a bond directly between the carbon and oxygen. Now we are just going to find the formal charge of the oxygen, but in order to do so, I'm just going to, in order to make the things more vivid, I'm just going to show them with the bond with the C2H5. It doesn't make any difference, but because I'm just going to draw my fishing net, that's the reason I'm just showing it that way. Now, I'm going to draw the fishing net around the oxygen now in order to find the formal charge. And in order to do so, what I'm going to do that, I'm just going to ask myself again two questions. I'm looking at the oxygen to find the formal charge on it. I ask myself, what is the formal charge? What is the address of the oxygen in the periodic table? All we know that it comes with the electron number 8, then it comes with the group 6 of the periodic table. It comes with the group 6. I put the group 6 over there. Then what I'm going to do is this, that I'm just going to ask myself that how many electrons I have inside the net which I have drawn. You see 1 electron is there. 1 electron is there because you remember each extended line in the Lewis structures represents 2 electrons, 1 to the left, 1 to the right. If you have your net around the oxygen, you're crossing these lines at the middle, then it means that you have a share of 1 inside. Now also I have 1, 2, 3, 4. Okay? I have also, look at that, I have 1, 2, 3, 4, 5, 6. Then I have also 6 here, okay? Which it means that the oxygen which I had also there comes with the effective charge of the 0. 6 at the group that it belongs to, and you see 2 lone pairs give me 4, 5, 6 electrons. 6 minus 6, it just gave a neutral charge also to the oxygen that we had over there. Now, then we see that by doing this, what we have done, we formed this compound. Which was ether format. We are not going to discuss about the functional group at this stage, but only thing which we needed to show was that what happens if we just produce stones from here, we can get the output. The purpose was that to show how the reaction is going to proceed, but in the meantime, before we finish, remember we had the bromide from the leaving group and we had the sodium from the sodium ethoxide. In the presence of this one, they can come to an equilibrium. We form sodium bromide, which will become a kind of an aqueous in the salt becomes like the aqueous format there. Now, in the next part of the tutorial, we are just going to see what is going to be the output if we introduce heat to this reaction, which makes a completely different pathway for the reactivity. Okay, now we come back with the second part. Previously, what we discussed, it was a substitution nucleophile for this reaction. Now we notice that I'm just going to input some heat into this reaction. You are going to see what is going to be the implication of this heat, because it's just going to completely change the direction of the reactivity for this reaction. Now, first of all, the thing that I said, we have to find empty orbitals, welcoming the migrations of the lone pairs of the electron, and find somewhere a lone pairs of the electron willing to migrate. Now, that's the key that we have to solve. First of all, we look into this one as previously. We noticed that the bromide is a good leaving group. Because of the huge contrast of the electronegativity, it can take away all the shared electrons between the carbon and itself, then end up somewhere here as a bromide with 4 lone pairs of the electron, which becomes a negatively charged. Then what do we end up here as previously is that we just end up with this structure. With the central carbon, which is attached to 3 methyl groups, which now we can say that, okay, it becomes positively charged. And I discussed that in the previous lecture, that why it becomes positively charged. To form a carbocation or the electrophile, you know how to find the effective charge for it based on the previous tutorial that we had. However, there is one minor thing that we have to discuss. First of all, we know as before also that the sodium ethoxide in the presence of the ethanol, it can just deionize itself. Then what do we have here is that we have C2H5 oxygen with 3 lone pairs of the electron, which you know again from the previous lecture, why it becomes a negatively charged? To form a very, very strong Lewis space. To become a Lewis space. But at the same time, there are 2 terminologies I want to introduce to you. The first is this. I said that the carbocation that we have there, also I know that it's a tertiary carbocation because it is directly connected to 3 carbon which is adjacent to that. It becomes tertiary carbocation, and due to the concepts of the hyperconjugativity, you're just going to see that this becomes very structured because overlapping of the orbitals of this one into an empty orbitals make these structures significantly more stable compared to the primary or secondary carbocation. I'm not going to go into that more details in the theories, but I'm just going to call this carbon alpha carbon, and the carbon adjacent to that, I'm just going to call them beta carbon. Now, then look at what's going to happen. I'm looking to this factor, and I'm going to say that, okay, if before the heat was happening, we noticed that there is a nucleophilic attack. That's what we discussed. But here, when we have the presence of the heat, I'm just going to show peculiar structure. I'm just going to say that, okay, if CH3, I can show that with the expanded structures with the hydrogen. This is the same thing as CH3, but I expanded CH3 into 3 hydrogen covalently bound to the carbon which I had there. Now, when the heat is present, although we still have the nucleophilic attack to a lesser degree, but the more important thing is that the heat which we had over there, it just mixed the beta carbon with the beta hydrogen that we had to become loose. What does it mean? It facilitates to removal, a breaking of this bond. You remember from the basic chemistry classes that when you form a Lewis bond, you give the energy back to the environment, but when you are just going to dissociate the Lewis bonds, you have to spend the energy in order to break the bond. And the energy that you are putting in terms of it into this structure, it causes a cleavage of this bond. Then if the bond is going to be broken, it's going to be heterolytic. It means that the lone pairs that you had there, it just migrates either to the hydrogen or carbon. It's impossible to get the hydrogen with the electron, to get the hydrogen with the negative charge, because it has almost a very negligible electronegativity. It's impossible that you have this. Then as a result, the lone pairs of the electron that is going to expect to migrate, it just gonna goes to the carbon. Now, at the same time, the hydrogen, which is going to get loose, there is no electron, it becomes protonally, becomes hydrogen ion, it's just going to be taken away by the Lewis space that we had. Then what do you have here? From these structures, you are forming the ethanol, which goes back as a solvent into these structures. But at the same time, look at these structures which we have. It's not going to happen like that, but I'm just going to show that to demonstration. I'm going to show that to you. We have carbon here. Let me show the central carbon which I have here. The central carbon. I have the methyl group this end. I have the methyl group this end. I have the carbon here. I have 2 hydrogen there now. I have 2 hydrogen here. The third hydrogen was removed. You see that you dissociated the bond. And as I said before, when you dissolve a bond, you have to stop and ask yourself a question. What is the effective and formal charge of the elements that they are directly impacted by dissolving of the bonds which happen to them? You see that the carbon was directly impacted. I have to find the formal charge associated with it. Then you see that, okay, then in that case, you have this one. I drew a net around that. I asked myself 2 questions that before. The first question is that, what is the address of the carbon which is directly impacted by the bound cleavage? By the address, I mean the groups in the periodic table. You said it's group 4. Then I'm just going to write it here. Then also, remember, you had the electrons just moved inside. I'm just going to put these 2 electrons there. 4. Then you ask yourself the next question. How many electrons? These 2 electrons is the electrons which is cleaved from the hydrogen. How many electrons inside the net? You see you have 1 electron here, you have 1 electron here, you have 1 electron here, becomes totally 3. And you have a lone pair, 3 plus 2 gives you 5. When you subtract 4 minus 5, it gives you -1. When you see that, then as a result, you are not going to form a carbocation, you're going to form a carbanion, which is incredibly volatile and unstable. Carbon with a negative charge is incredibly short-lived and negative. It has to push away the electron which is causes the negative charge on the carbon. Then I'm just going to erase the net which I have created there. Then I notice that, okay, then the carbon which I formed there becomes carbanion. It's very volatile and short-lived. And the only solution for this short-lived structure is that because energetically it's so high, you have to kick away the source of the negative charge on the carbon. What is the source of the negative charge on the carbon there? The lone pair that you just give it to it. Then you have to just kick it away. In order to kick it away, and also still remember, I forgot to just put this carbocation here because this is still positive. In order to kick it away, to remove the carbanion presence, the best way is that you just give it as a pi bound between these 2 adjacent carbon. One of them is a carbon, alpha carbon. This is beta carbon. This is carbocation. This is carbanion. And by giving them a double bound nature to that, you are going to see that you have the central carbon here. You are creating CH2 over there. You have a CH3 here. You have a CH3 also here. Then you are creating this product, which we call that alkene, because it has a double bond associated with it. Okay? Now, then you see that by doing this, look at that. We formed another bond between 2 elements. We formed a bond. Now again, the same scenario. We have to stop to decide what is a formal charge associated with all the elements which are directly impacted by the formation of the bond. I go with this one. If I draw the net, I see 2 electrons comes from the hydrogen. Let me show you it in that way, because it makes it much easier to see the formal charge associated with it. I'm just going to put the hydrogen there. And that becomes the double bond. That's why I'm just going to show it like that. Now, for the carbon which is adjacent, impacted, I'm just going to draw my fishing net first. I'm going to ask myself first, what is the address of this carbon? It comes with the group 4. How many electrons inside my fishing net? I see I have 1 electron here, 1 electron here, 1 electron for this bond, 1 electron for this bond, 4. I got 4. Then I have 4 minus 4 becomes 0. The previously unstable carbanion becomes now neutral, becomes more stable. Now, the other thing which I'm going to do, another carbon which is impacted by this, if you notice, it's the previously carbocation which we had. I'm going to do the same thing. I'm just going to draw my fishing net around the carbon which is impacted. Ask these two questions. What is the address of this carbon in the periodic table? 4. How many electrons inside net which I have? I have 1 electron here, 1 electron there, 1 electron there, and 1 electron there. This is, you see that these dots becomes 4. Then I have 4 minus 4, it also becomes 0. Then as a result, the previously carbocation, by pushing the electrons to form a pi bond, it also becomes neutral. Then you see that. By this strategy that we did, let me erase this. By this strategy that we did, by forming this double bond, we were able to do what? We were able to form a structure which in terms of the energy, which is squashed, the energy brings down, and this one becomes the most stable structures because you have removed both carbanion and carbocation by forming a double bond between them. This happens just because of the presence of the heat that you introduce to the reaction. If the heat was not present, you only get what? You only get the ether products that we had through the substitution reaction. This one, which we eliminated 1 hydrogen there, which we call that elimination reaction, which we are just going to have more examples there. In the next step that we are just going to show, we are going to see that what is going to be the impact of the solvent itself. Can the solvent also play the role into the reactivity? And that becomes the third part of this tutorial when we focus more on the presence of... Okay, now for the very last part of this tutorial, we noticed that so far we had 2 outputs from the first substitution nucleophilic reaction, from the elimination reaction, which we saw that depends on the presence of the heat, which is going to be symmetric. It doesn't matter which beta hydrogen you take, but all these 3 options in elimination products give you the same product because of the symmetry which exists. Now the third part and the last part of this tutorial is that what happens if just the solvent itself, which is ethanol, and it's a polar protic solvent because it has 2 lone pairs of the electron. What happens if itself reacts with the substrate that we have? First of all, what is the necessity of this consideration? Because you remember that with the presence of the solvent itself, which entices and reduces the transition state energy, we notice that the bromide, which is the good leaving group, is going to depart. If this happens, what do we may expect? We again, like before, we have the central carbon, which is going to be the tertiary carbocation, which is very suitable for SN1 reactions, but I'm not going to talk about the kinetics at this stage. I'm just going to show only the path that you're just going to conduct a reaction, and you notice that you're just going to have a carbocation there. But at the same time, I'm going to focus my attention on the solvent, not the reacting agent, which is sodium ethoxide, because I say that there is a 2 lone pairs of the electron on the hydroxyl group of this alcohol, which can also be a mobile lone pairs in order to orchestrate the reaction. Because our goal was to find the electron pairs which can just move around in the products that we have. Then as a result, I'm just going to have this one. For example, I have the solvent itself, which has 2 lone pairs of the electron. One of them I'm going to show that distincted with the red color, which I'm just going to show that later why. And we see that the solvent that we have, which is the polar protic solvents, it can here again act as a very strong Lewis base, because it can have those electrons move. And the electron pairs that we have over here on the hydroxide, it can just find itself in close vicinity to the carbocation in the solvent, which is itself, to attack this carbocation. And the arrow which I show, it shows the direction of the migrations of these lone pairs into this one. If this happens, what do we may end up with? We may end up with this reaction. I have the central carbon, CH3, and around it, I'm just going to show you with a different color, the lone pairs, which is denoted here in red. It's just going to form this bound I'm going to have the oxygen, which is the bound because the lone pairs is on the oxygen. When you form a bound, it's oxygen that is going to be connected. I have the hydrogen, which it was previously here. And also, what do I get? I had the rest of it. C2H5. Let me make it a little more clear. We have C2H5. Now, and also I do not forget, one lone pair is spent to form a bound. The second lone pair is just going to remain intact. What we did before was that we noticed that whenever we form a bound in organic chemistry, we have to stop and find the formal charge. The formal charge, which you're just going to get it for the carbon, it's just going to be neutral because you draw your net around carbon. You see you have 4 electrons around it. Carbon is from the group 4 of the periodic table. 4 minus 4, it gives you 0, which it means that it's going to be neutral, the structures. But when I come here with the other elements, which is directly impacted by this bound, this is the oxygen. I'm going to draw the net around it to find the formal charge on the oxygen. When I do this one, I see that I have to ask myself 2 simple questions. The first question is that, what is the address of the oxygen? By the address, I mean its group in the periodic table. Everyone says that this is group 6. Now, and also, I'm just going to go to see how many electrons I have inside that. I have 1 electron there. I have 1 electron here. I have 1 electron here. Because each Lewis bound, when you draw a net, it gives 1 share of the electron to that element. I have 3 electrons, and 2 electrons there becomes 5. I subtract them together. 6 minus 5, it gives you plus 1. Now, which it means that the formal charge of the oxygen after this new substitution reaction, it becomes essentially what? A plus charge. This is a problem for us in organic chemistry. Because remember, we have always seen that the oxygen, it's highly electronegative, one of the most electronegative elements in the universe, which it means that it has to overflow with the excess of the electrons. Then you expect to have a negative charge on the oxygen. But here we show positive charge, which signifies the electron deficiency. You have electron deficiency for an element which is highly electronegative, and it's not going to be tolerated in organic chemistry. Then you have to find a solution for it. The solution that we can find for it is this. Again, because we have the solvent in the reaction, we can remove this. We have 2 paths. We have 2 parts of the solution to do that. Either I'm just going to break the bound, which I'm just going to go back all the way up there, which is not logical. The other thing which I can do that is this. I'm just going to look at that. The bound between the hydrogen and oxygen is extremely polarized. Now, then as a result, in the solvent, with a little bit of the heat, you can just remove this bound between the hydrogen and oxygen, because hydrogen, when it comes to fighting over the electron, in the presence of the oxygen, has no strength. If you have oxygen suffering from the electron deficiency, and there is a hydrogen is going to lose the fight. He's going to give back all the electrons to the oxygen, and itself becomes like what? Becomes like the hydrogen ion. And don't forget also the presence of the bromide that we had before also, after the leaving group. We're going to talk about that, what happens then. Then as a result, if this happens, what do we end up with as a final product of the solvent reaction? We have the carbon, the central carbon here. We have CH3. We have the oxygen. And we have CH2H5. We had the lone pair there. The lone pair from the cleavage of this bond also is going to be given back. We have this one there, which essentially you see that this is the same products that we had. The same products that we had in the tutorial 1. I'm just going to call that product C. You see that products A, which we had in the first tutorial, in the first part, and product C exactly are the same, And that was the reason when I started tutorials, I highlighted down, look at the structural resemblance between the reacting agents, which was sodium ethoxide and with ethanol. You see that the Z2H5O, they are the same thing. And that's the reason that you have. When the solvent reacts with the product itself, because it has low impurity of the electron, it's as if the reaction happened with this one. Then you may wonder if the reaction was happening, let's say, in isopropanol, or for example, methanol, butanol, any other solvents, the solvent lysis which we had, part C is a result of the solvent lysis. When the solvent reacts with the product, it's called solvent lysis. Then you could have seen that the output through the solvent lysis was become significantly different than the initial reaction. And that's the reason you see the structural resemblance of the solvent with the reacting agent, because we didn't want to have another type of the output in our product. That becomes this. And also, you may have wondered what happens with the hydrogen there and also the bromide which we had there. Then we can form the HBr. I'm going to write it here very quickly. HBr is formed because that's positive, it's negative. However, it's not going to be sustained because hydrobromic acid, it's very strong. Then when you have it, when it forms, then it reduces to the hydrogen and bromide in an aqueous format. You see, it reaches to equilibrium, but the equilibrium extends itself more towards the right than you have this ion. Then as a result, when you form the hydrobromic acid in this solution, due to the concepts of the Bronsted lower definition of the acidity, you're going to see that hydrobromic acid is just going to be deionized itself because that's the very strong Bronsted acid. Then now, we are reaching to the end of this tutorial. Then you saw that without getting involved too much with the kinetics, we find a clue that how to just start to orchestrate the reactivity when we have the low impurity of the electron anywhere in our reaction. We were able to form 3 outputs, that the third one was the same with the first one due to the fact that the solvent lysis happened because of the structure of the resemblance that we had with the reacting agent. And that finalizes our tutorial for today.